Hi everyone! Welcome to part 5 of chapter 16. Today is our last lecture on our chapter in acids and bases. We have a couple random topics left to cover and then that will be it for this chapter. So let's go ahead and get going. So our first topic today is the ionization of polyprotic acids. And so polyprotic acids are acids with more than one acidic hydrogen. So this would be, like sulfuric acid, or phosphoric acid, where they have more than one hydrogen that's acidic. And I want to point out that not all hydrogens in an acid are always acidic. For example, if you have something like acetic acid, right, only this first hydrogen here is acidic, meaning that it will ionize in water. These other three hydrogens are not because they are attached to the carbon, and the electronegativity difference between the carbon and the hydrogen is not large enough for these hydrogens to be acidic. So these over here in sulfuric acid and phosphoric acid, those hydrogens are attached to the oxygen, and so the electronegativity difference between the oxygen and the hydrogen is much larger, and so those are acidic hydrogens. If we want you to know that a hydrogen is going to be an acidic hydrogen, typically it's written in the front like this. And so since there is more than one, right, we have H2SO4 and H3PO4, that's going to clue you in that these are polyprotic acid. So many protons is essentially what it means. And so these acidic hydrogens ionize in steps. They don't all come off at once. It's not like an ionic compound where they completely dissociate in water. One of the hydrogens will ionize first, and then the other, and then, if there's three, then the one after that. And each of those hydrogens has a separate Ka value. And the first hydrogen to come off is always going to have the largest Ka value. That one is going to ionize the most. And then the next one will have a smaller Ka, and if there's a third one, that will have an even smaller Ka. And generally, the way that this plays out is the difference in all of these Ka values is so large that the second or, the third ionization doesn't happen to a large enough extent to even affect the pH. So usually for all of these polyprotic acids, we are just going to ionize them once. So like sulfuric acid, well, sulfuric acid is not a good example, and we'll talk about that in a minute, but we'll say phosphoric acid, we are just going to look at the first ionization. So pulling off one of these hydrogens and ionizing water. Okay, again, the other ones do ionize. They just don't ionize enough to affect the pH as much as this first one does. And so sulfuric acid, like I said, I was going to use it. It's kind of a bad example. The only exception to this is sulfuric acid. And the reason for this is that sulfuric acid is a strong acid. And essentially, we're going to use our concentration of sulfuric acid as our hydronium ion concentration for the second ionization because it's a strong acid. And I'll show you what that looks like in a minute. But for all other polyprotic acids other than sulfuric acid, for all of the other ones, we are just going to ionize them once because Ka1 is so much larger than Ka2 and 3. So here's some polyprotic acids. Again, like I said, sulfuric acid's a strong acid, so we don't even give a Ka1 value, but it does have a Ka2, and so that would be what we would use for this calculation. We're going to talk a little bit more about that in a minute. But if we look at, let's say, phosphoric acid, since we were just talking about it, Ka1 is much larger than Ka2. Look, times 10 to the minus 3 versus times 10 to the minus 8, and then times 10 to the minus 13, right? So the hydronium ion concentration, that's from these is going to be negligible compared to the first Ka value. So again, for most of these, when we're writing these, we're trying to find the pH of these polyprotic acids, we're typically just going to use that first Ka value. All right, back to sulfuric acid. So again, sulfuric acid is a strong acid, so when it reacts with water to produce HSO4 minus and hydronium, right, we are going to say that all of this breaks apart into two pieces, right? So our initial concentration of sulfuric acid is going to be equal to our concentration of H3O plus and of this bisulfate. Okay. And then because now this is still a weak acid, right? It still has an acidic hydrogen on it. So it can react with water again to produce sulfate and hydronium ion, right? So our initial concentration, that was what we were talking about before, this initial concentration of hydronium, and then we can add it to the rest of this one to figure out our pH, okay? And this, right, like has a Ka value. We can do our whole equilibrium concentration to figure out the concentration of H3O plus. For these sulfuric acid solutions, the second ionization is significant and must be accounted for. And like I said, the reason for this is that this first Ka value is so large, it completely dissociates, and this is still a pretty good acid, right? Times 10 to the minus 2, that's a pretty strong, weak acid still. And so since we have a strong acid for that first one and a pretty strong weak acid for that second one, we need to take both of these into account when we are calculating the pH. So our sulfuric acid that we started with, because it completely dissociates, it's going to break into this bisulfate and hydronium ion. And then we can use this concentration to do our equilibrium concentration to figure out the concentration of H3O plus from that and add it together with this initial one to get our total H3O plus. And then we can go ahead and find the pH by taking the negative log. Okay, so sulfuric acid is our one exception for our polyprotic acids. So here's a different polyprotic acid. And again, we have our acid. It's going to react with water, and we're going to pull off one of the hydrogens, and then that can react with water again and pull off another hydrogen, right? And to figure out our total hydronium ion concentration, we would figure out the amount of hydronium from the first ionization and then the amount from the second ionization and add it together. But as you can see, right, our contribution from the second ionization is so small, right? Times 10 to the minus 12 versus times 10 to the minus 3, that this is negligible. It doesn't change the amount. And like I said, this is why we're just going to typically use that first ionization and not worry about any of the others, because even though they happen, it doesn't happen to enough of an extent to affect the pH. All right, let's go ahead and do a practice problem. I want you to write balanced chemical equations for the sequence of reactions the following polyprotic acids can undergo in water. So essentially, I want you to show me all of the ionization reactions that can happen for these acids when they react with water. So go ahead, pause here, and then come back when you're ready. All right. So let's go through this. So this is sulfurous acid, not sulfuric acid, right? And this is a weak acid. And so in our first reaction, that sulfurous acid will react with water, and it will lose one of its hydrogen and produce H3O plus. In our second reaction, we're going to take this ion and we're going to react it with water again to produce sulfite and the hydronium ion. Okay, so in each one of these reactions, again, we're just taking off a hydrogen and we're donating it to water. For phosphoric acid, we're going to do the exact same thing. In the first one, we'll donate one of our hydrogens to water, and then we'll make this ion. In the next one, we'll take that ion, pull off another hydrogen, and then we'll pull off yet another hydrogen in that third reaction. Okay, our next topic is talking about acid strengths of binary acids. So I've talked a little bit about the fact that hydrofluoric acid is the only the only halogen acid that is a weak acid, right? All of the other ones are strong acids. And so now we're going to talk about why this is. So I have two different trends that I want to talk about with respect to binary acids. And so remember, something is a binary acid if it's bonded to, if it's hydrogen and just one other element. It can be multiple hydrogens, but it has to be just hydrogen and one other element. So like technically water is considered a binary acid, right? Remember, water's amphoteric and can act as an acid or a base. And so it's got, two hydrogens and then bonded to oxygen. But again, it's hydrogen and one other species. Okay, so these are the ones we're going to look at. There are more. Okay, and so our two trends are with respect to electronegativity and radius. Okay, so the more polarized the bond end is, the more acidic the hydrogen is. Okay, so this difference in electronegativities, it's what's going to come into play going from left to right. So as we go from left to right, we are going to increase the electronegativity of the atom that's being bonded to the hydrogen. Okay, so like fluorine is more electronegative than oxygen, chlorine's more electronegative than sulfur, bromine's more electronegative than selenium, right? So as we increase the electronegativity, we are increasing the polarity of our bond, right? The electrons are shifting away from the hydrogen. So as we shift the electrons away from the hydrogen, that makes the other atom more electronegative, right? And our hydrogen becomes more electropositive. And so the larger that partial positive charge on that hydrogen, the more acidic the hydrogen is, the more likely it is to be attracted to the water molecule. Okay, so as we go from left to right, we are increasing the electronegativity difference between the hydrogen and the other atom, and that will increase the strength of the acid. That will make it more likely to dissociate. You can think about this kind of like with respect to ionic compounds. Like if you think about sodium and chlorine, there's a very large electronegativity difference between those two atoms. And when you put sodium chloride in water, it completely ionizes and doesn't even try to stay together as sodium chloride because it's such a great electronegativity difference between those two atoms. They're more attracted to the water molecules than they are to themselves or to each other. Same kind of thing is happening here. As we increase the electronegativity difference between the hydrogen and the other atom, the hydrogen becomes more positive, the other atom becomes more negative, and essentially they become a little more like an ionic compound, right? And so that makes it easier to break that bond, and that will make it more acidic. Remember, more acidic means it is more likely for that hydrogen to be donated to water. So our binary acid strength increases going to the right across the period. So for this row, it would be, carbon-hydrogen bond, which is essentially very non-polar, right? It would be very, not really acidic. And then the nitrogen-hydrogen bond, oxygen-hydrogen, and then hydrogen fluoride. Okay. So that would be, as we go from left to right, we are increasing the strength of the acid. And then our other trend that we're looking at, it says bond strength here. And the reason that this is going to be bond strength is due to atomic radius. Okay. As we increase the size of the other atom that's being bonded to the hydrogen, the nuclei get farther and farther and farther apart, right? The distance between the hydrogen nucleus and the other atom's nucleus becomes farther and farther and farther apart. And when that happens, that is weakening that bond. And as we weaken the bond, right, that makes it easier for that hydrogen to ionize. It makes it easier for that hydrogen to become donated to water. So we are decreasing the bond strength as we go down the period. So as we go down the period, we are weakening our bond, which means that it is becoming a stronger acid because it's easier for the acid molecule to break apart. It is easier for the acid to donate its hydrogen to water. So in this group 7A, right, so that's our halogens that I keep talking about. Hydrofluoric acid is our weakest and hydroiodic is our strongest. So this is why hydrofluoric acid is a weak acid, even though there's a very large electronegativity difference between hydrogen and fluorine, which would make it fairly easy, right, for that, that hydrogen to ionize. Because fluorine is so small and hydrogen is so small, their nuclei are fairly close together, and so that is contributing to the strength of the bond. So even though they have this large electronegativity difference and it's really polar, right, because it's a small enough molecule, right, that atomic radius or the distance between those nuclei is so small, it's not strong enough to ionize completely in solution. So it's a really strong, weak acid. So here's just a little bit of data, like hydrofluoric acid I was talking to you about is a strong bond because those atoms are similar in size, right? And fluorine is a really small atom, hydrogen's a really small atom, so they have a fairly large bond energy. Whereas chlorine and bromine are both larger atoms, and as you increase the size of that molecule that's being bonded to the hydrogen, you are weakening the bond. And as you weaken the bond, that makes it a stronger and stronger acid, because it is easier for that hydrogen to fall off the molecule. It's easier for that hydrogen to ionize. All right, let's go ahead and do a practice problem. So for each of the following pairs of acids, determine which would be expected to be more acidic in an aqueous solution. And then I want you to explain your answer. So go ahead, pause here. It may be helpful to look at a periodic table while you do this. And then once you figure out your answer, come on back. All right, let's go ahead and go over this. So here we have hydrogen bromide and hydrogen selenide. So let's see. If we look, they are in the same period. Okay. If you're looking at the periodic table, we have selenium, and then we have bromine. And so when we go from left to right like this, our trend is going to be in our differences in electronegativity. And so as we get to be the other atom that's being bonded to the hydrogen, as it becomes more and more electronegative, that makes the difference in the electronegativity values between the hydrogen and the other atom greater. And as we increase that electronegativity difference, we make the bond more polar, which means that it is easier for the hydrogen to ionize. So the bromine is going to be more electronegative than selenium, which means that it is going to cause the stronger, or create the stronger acid. And then the other one, hydrofluoric acid versus hydroiodic acid, if we look, we have fluorine up at the top, and then we've got, chlorine, and then we've got bromine, and then we have iodine down here. So again, our trend in for a given column, for a given group, is based on atomic radius. And so the larger the atom is that's being bonded to the hydrogen, the weaker the bond between the hydrogen and that atom. So since iodine is so much larger than fluorine, that's going to cause a very weak bond between the hydrogen and the iodine. That makes it easier for the hydrogen to ionize in solution, so which makes it a stronger acid. Okay, so these are the two trends that I want you to know. From left to right, this is due to electronegativity. And from up and down, it's going to be to atomic radius, which again causes the bond to weaken. As you get a larger atom, that will cause a weaker bond. All right, so now we're going to talk a little bit about the strength of oxyacids. So we were just talking about the strength of binary acids, where it's hydrogen and one other atom. And then now we're going to talk about the strength of oxyacids, which is going to be a hydrogen bonded to an oxygen, which is bonded to other stuff. Or the hydrogen might be bonded to that other atom, which is bonded to some oxygen. But in general, we need to have hydrogen, oxygen, and other things. Okay. So our first bit is that the more electronegative the other atom is, the stronger the oxyacid. Okay, so if we look at these two, right, the only difference between these is that we've swapped out the chlorine for the iodine. Okay, chlorine is much, much more electronegative than iodine is. And so what happens is, since the chlorine is more electronegative, it's pulling the electron density away from the hydrogen, right? And as we pull the electron density away from the hydrogen, we're making that bond more and more polar, just like we were talking about with our binary acids. As we increase the polarity of that bond, right, we're making it a little more like an ionic compound. And so that means that the hydrogen is going to be easier to ionize in solution. So the more electronegative that atom is, the more it's going to pull the electron density away from the hydrogen, making it easier for the hydrogen to fall off, which makes it a better acid. So our other one is the larger the oxidation number on the central atom, the stronger the oxyacid. Okay, and so this will require you to be able to calculate the oxidation number. If you've forgotten how to calculate the oxidation number of the central atom, you might want to check it out. But essentially, since we're just dealing with hydrogens and oxygens right now, you just need to figure out essentially what the kind of charge on your atom would be. Remember that hydrogens are always worth +1 and oxygens are always worth -2, unless it's in a peroxide, and then it would be a -1. Here, we're not going to have any peroxides. We're just going to say, hydrogens +1, oxygens -2. So if we look at carbonic acid, our oxygens are going to be a total of 6-, our hydrogens are going to be a total of 2+. This is a neutral molecule, which means the carbon is going to be a +4 or 4+. Whereas if we look over here, we have a 3+ from the oxygen or from the hydrogens, a 6- from the oxygens, which means that boron is going to be a 3+. So our carbonic acid is going to be stronger than our boric acid because carbon has a larger oxidation number on that central atom. Okay, and then finally, our last one, which we see a lot, the more oxygens that are attached to this Y molecule, right, this other atom, the stronger the oxyacid. Okay, and so this one we will actually see quite frequently. So the more oxygens we have on that central atom, the stronger the bond is. And essentially, it's going to work by continuing to pull the electron density away from the hydrogen. The oxygens are really, really, really electronegative, and so it's going to shift the electron density in the entire molecule further away from the hydrogen. And as we do that, we're increasing the polarity of the hydrogen bond onto the molecule, and as we do that, that increases the acidity of that hydrogen, making it a stronger acid. So here we go. So if we look, if we have hydrogen, oxygen, and then something, right? As we increase the acidity, as we increase the electronegativity of this other atom, we make the acid stronger and stronger and stronger, right? So chlorine is going to be the most electronegative, and then iodine's the least if we're looking at these halogens. And as we increase the electronegativity of the other atom, we are making the acid stronger and stronger and stronger, right? If we look at these Ka values, this is going to be the largest Ka value. Even though it's still relatively small, it's the strongest of these three, and that's because chlorine is the most electronegative. And so chlorine is going to go ahead and shift the electron density in that molecule closer to the chlorine, right, further from the hydrogen. It's going to make this bond more polar, and as we do that, right, as we increase that electronegativity difference, we pull the electron density away from the hydrogen. That is going to make this hydrogen more acidic and easier to ionize. Here's the one where I was talking about the oxygens on the central atom. As we get more and more and more oxygens on the central atom, like up here we have, at the top we have 4 all the way down to 1 at the bottom. As we have more oxygens on the central atom, we're pulling the electron density away from the hydrogen. Like all of the electron density in the molecule starts pulling that way because those oxygens are so electronegative. And so the more oxygens on that central atom, the more we can pull the electron density, which is going to shift the electron density out of this bond, which weakens that bond and makes this hydrogen more acidic. Okay, so just the name of the game in general, guys, is to look at the electronegativity of the species and see if it's, which one is going to pull the electron density away from the hydrogen the most. And whichever compound pulls the electron density away from that hydrogen the most, that will be the strongest acid. So whether it's these, and we're just looking at the electronegativity of the halogen here, or whether we're looking at the number of oxygens, it's kind of making the same end result. We're still pulling electron density away from that bond. We're weakening the bond, making it easier to ionize that hydrogen. All right, let's go ahead and do a practice problem. So we have a bunch of pairs of acid, and I want to know which would be expected to be more acidic in an aqueous solution. So I want you to pause here, pick which one's going to be most acidic out of the pair, and then explain your answer. Okay, so for this first one, we are looking at the electronegativity difference between bromine and iodine. Since bromine is more electronegative than iodine is, bromine, right, the acid with the bromine in it will pull the electron density away from that hydrogen the most, which will make the hydrogen more acidic and easier to ionize. For the next one, we're looking at the number of oxygens on the central atom, right? The number of oxygens that are on the sulfur atom. Since sulfuric acid has more oxygens on the central atom, it's going to pull that electron density away from those hydrogens more than sulfurous acid, right, which only has 3 oxygens. And as we pull the electron density away more, we make that hydrogen more acidic and easier to ionize. And so for this last one, we are looking at the electronegativity of the central atom itself. Rather than looking at, the halogen that's being bonded on, we're looking at the central atom itself. Since sulfur is more electronegative than carbon, right, we're the same kind of thing. We're going to be better able to pull the electron density away from the hydrogens and make them easier to ionize in solution, which makes it a stronger acid. All right, this is the last topic for the chapter, Lewis acid-base theory. So we've already talked about 2 different acid-base theories. We've talked about the Arrhenius acids and bases, and we've talked about Bronsted-Lowry acids and bases, right? And so for Arrhenius acids and bases, we were looking at acids produce H plus in solution and bases produce OH minus in solution, and we said that was really good for strong acids and strong bases, but it wasn't as helpful for weak acids and bases. With Bronsted-Lowry, we were looking at proton transfer, right? We were looking at, acids being proton donors and bases being proton acceptors. So, but these both required that hydrogen, right? We were always looking at what's happening with the hydrogen. Is it, being donated or is it being accepted? Well, Lewis acids and bases don't focus on hydrogens or hydroxides or anything like that. They are looking at an electron pair. Okay, so we're looking at one pair of electrons. What is that doing? So a Lewis acid is going to be a lone pair acceptor. Sometimes you'll hear this called an electrophile, especially in organic chemistry. But a Lewis acid is a lone pair acceptor, and then a Lewis base is a lone pair donor, and this will be called a nucleophile, again, also used in organic chemistry. The cool thing about Lewis acids and base theory is it doesn't require any hydrogens. So now we can look at acids and bases in a totally different way. All right, so Lewis acids. Lewis acids are always going to be electron deficient, which means that they don't have quite as many electrons as they would like to. And so this could be for a variety of reasons. It could be because they're attached to a really electronegative atom, and so the electron density is being shifted away from that atom. Or maybe they don't have an octet. Maybe they're a boron molecule or aluminum, right? And they've only got 6 electrons around it instead of 8. So Lewis acids, in order to be a Lewis acid, they must have an empty orbital that's willing to accept the electron pair. So for some reason or another, they need to be short on electrons, and because Lewis acids are going to be electron acceptors. So for example, we have hydrogen would have like an empty 1s orbital. Boron in boron trifluoride has an empty 2p orbital. It has an incomplete octet. It's only got 6 valence electrons instead of 8. That makes it a really good Lewis acid. Silicon tetrafluoride, silicon can expand its octet, right? And so even though it currently has an octet, it can expand its octet, and so it can still accept more electrons. So those are the 3 ways it really shows up. Many small, highly charged metal cations have empty orbitals that they can use to accept electrons, so they become really good Lewis acids. But again, it's going to be very small, highly charged cations, not like sodium or something like that, but copper or iron, right? Any kind of transition metals usually are going to be good for this. And then we can also have atoms that are going to be attached to highly electronegative atoms and have multiple bonds, like carbon dioxide. So carbon dioxide looks like this, right? And so that carbon has a lot of its electron density being pulled away from it. Both of those oxygens are really electronegative, and so they're going to shift the electron density towards the oxygens and away from the carbon, making that carbon really electropositive, right? It's really electron deficient. So this carbon can be a good Lewis acid because something can add on to the carbon. And since carbon has double bonds, if it got more electrons, which was going to push it over 8, which, right, carbon can't expand its octet. It's not in the third energy level. So if carbon was going to add on some more electrons, it solves that by it just kicks some of these electrons over to the oxygen. Okay, so the carbon in carbon dioxide can be a good Lewis acid. Same thing with sulfur dioxide or anything like that. But they have to be kind of electron deficient, right? Because they've got some of those electrons being pulled away from them, right? Because they're attached to highly electronegative atoms. And they need to have these multiple bonds so that they don't go above their octet if they can't expand their octet. Lewis bases have to have electrons that they're going to give away or share. And so usually the way that this works out is the Lewis base will have a lone pair of electrons on it that it can donate. So this would be things that have like nitrogen or oxygen on them, because if we think like ammonia, right, ammonia has this lone pair on the nitrogen. That makes ammonia a really good electron donor, right, because those electrons are free. This is a pretty small molecule. It's not really going to be hindered at all. And so those electrons are easy to donate to a Lewis acid. In general, anions are going to be better Lewis bases than neutral atoms or molecules because they've got more electron density and they have an overall negative charge. And then generally, the more electronegative an atom, the less willing it is to be a Lewis base. And this is because if we have a really electronegative atom, that atom would like to keep the electrons for itself, essentially. And so if we have a really electronegative atom, it's not going to be as willing to donate its electron pair to another atom. So Lewis acid-base reactions are going to work kind of similarly to our Bronsted-Lowry acid-base reactions, in that in a Bronsted-Lowry acid-base reaction, we were, donating a hydrogen. We were having a hydrogen go from one thing to another. Well, here we have an electron pair that's being donated, but it's going from the base to the acid, whereas in Bronsted-Lowry, we were donating a hydrogen from the acid to the base. Okay, and so we don't usually get these electrons. The electrons don't move by themselves. Usually what happens is that the electrons on this nitrogen get donated to the boron and then they share them. Okay, and they form what's called an adduct. So before it was a base and an acid, right? And we know that this is the base because it has the lone pair, and this is the acid because it's going to accept the lone pair. And then afterwards they form an adduct. So this is a totally different type of reaction, right? We're not producing hydronium ions in solution. We're not producing hydroxide ions in solution. We're forming an adduct, okay? Arrhenius and Bronsted-Lowry acid-base reactions can also be classified as Lewis reactions. We are just focusing on this really specific type of Lewis acid-base reactions to see the difference. Okay. Most times when we talk about acid-base chemistry, we're going to look at Bronsted-Lowry acid-base reactions when we're looking at, what are the protons doing? Is it producing hydronium ions? Is it producing hydroxide ions? We usually keep that definition to that. And a lot of times we'll talk about Lewis acid-base reactions when we talk about these adducts. So here's another example. We talked about the first one already, but here's the Lewis acid, Lewis base example. Remember when in the last lecture we were talking about small, highly charged metal atoms becoming hydrated in solution. And so this is what's happening. That's a Lewis acid base reaction. So when we were talking about this in the last lecture, we talked about a Lewis acid-base reaction followed by a Bronsted-Lowry acid-base reaction when we talked about them reacting with water. Okay, so but this Lewis acid will react with this Lewis base, and form this adduct over here. Okay, this complex ion. So the aluminum, right, had a 3+ charge. It has lots of empty orbitals in which to accept these lone pairs. So we find this Lewis base, right, these oxygens, and they can donate their electrons to the Lewis acid and form an adduct. Here's another example. So again, we have the boron trichloride, right? It has an incomplete octet. That's going to be a Lewis acid. It's electron deficient. And then here we have these, the lone pairs on this oxygen that can be donated to the boron. And again, that's going to form our adduct. And then on this last one down here, we have carbon dioxide, which can act as a Lewis acid because carbon is electron deficient, right? Both of those oxygens that are bonded to it are electronegative, and they're shifting the electron density towards the oxygen and away from the carbon. So that makes our carbon really electropositive, right? It's very electron deficient. So this lone pair from the oxygen can be donated, right? It can act as a Lewis base and donate those electrons to the carbon dioxide, that Lewis acid, and then they can form carbonic acid, and we can do what's called a proton shift, where this moves around. This is organic chemistry. You don't need to know how to write the mechanism for this reaction in this class, but that's just letting you know kind of what's coming up. All right, here's a practice problem. I want you to determine whether each of the following species would behave as a Lewis acid or a Lewis base in a chemical reaction. It may be helpful for you to draw out the Lewis structure so you can see if it has a complete octet, if it has a lone pair, right? See what's happening in that molecule. So go ahead and pause here, figure out whether these would act as a Lewis acid or a base, and then unpause to see the answer. All right, let's go through this. So we have sulfur trioxide. This is going to act as a Lewis acid. Sulfur, even though when we form this molecule, right, if we were to draw out the Lewis structure, it would have an octet. And in some resonance forms, it would actually have more than an octet. But because sulfur can expand its octet, it can act as a Lewis acid, and it can add on more electrons to that sulfur and kick some of the double bonds out to the oxygen, forming single bonds and putting 3 lone pairs on the oxygen. So sulfur is very, electron deficient because it's bonded to these 3 oxygens that are really electronegative. So the electron density has been shifted away from the sulfur, making that an electron deficient atom, so it can act as a Lewis acid. Fluoride is going to be a really good Lewis base. It has, essentially, it just looks like this, essentially all lone pairs. So it can act as a Lewis base, and it can donate its electrons to a species. Phosphorus trichloride will act as a Lewis base because it has an available lone pair on the top, like that. I'm not going to draw the lone pairs on the chlorine, but phosphorus has a lone pair on it. It can act as a Lewis base. Aluminum chloride is going to act as a Lewis acid because if we were to, put aluminum chloride into water, it will break into Al3+, so it would be a small, highly charged cation. So that will act as a Lewis acid and accept some electrons. Methanol will act as a Lewis base because of the lone pairs on the oxygen. That oxygen can donate its lone pairs to something and act as a Lewis base. And then our magnesium will act as a Lewis acid because it's a small, fairly highly charged metal. And that is it for this chapter. We covered a lot of ground today and talked about a lot of different types of acids. We talked about binary acids, oxyacids, we talked about polyprotic acids, and then finally we talked about Lewis acids and Lewis bases. This is the end of this chapter. Make sure you're still working on all of those lecture worksheet problems. so that you can get the practice that you need to do well on the upcoming exam. As always, if you have any questions while you're working about the lecture or about any of the practice problems, please send them my way and I will be happy to help you. Otherwise, I will see you all next time when we start the next chapter.